Hello everyone, my name is Sang Yun Huang. We have three team members, including myself. The other two are Praktik Gupta and Venkata Tumurori. We are doing final project for natural language processing for healthcare from Georgia Institute of Technology. Clinical notes are healthcare documentation that are annotated by medical codes, which uniquely identify its patient's diagnosis, health condition, and treatment type. ICD-9 code is then the output from clinical notes, which is a classification of patient's disease. We need an automation tool to predict ICD-9 codes from clinical notes for the sake of improving efficiency and to minimize the human errors. Three machine learning techniques are then implemented to automate the prediction process, such as CNN, GRU, and LSTM. The purpose of our paper is to reproduce the results from the paper called Explainable Prediction of Medical Codes from Clinical Text. One additional tweak that we made is that we added LSTM model, which wasn't actually covered in the paper. For the data processing and cleansing part, we loaded MIMIC3 datasets into Hadoop 3.2, and then we did data processing using Spark 3.1. Discharge summaries corresponding to patient summaries are provided in node-events.csv, whereas all diagnostic ICD-9 codes and procedural ICD-9 codes are provided in diagnosis ICD and procedures ICD CSV files. For feature extractions, we use the word-to-vec embedding from Spark API. For all three models, we know that the embedding size is set to 100, and dictionary maps an integer value to the word embedding. The number of words in each document is limited to 500. The shape of the labels is a one-dimension tensor consisting of one hot encoding of each ICD-9 code tagged to corresponding summary. As we mentioned, we implemented three different models. Let's talk about LSTM first. In terms of parameter grid, these are the parameters that we set up. As we already mentioned, we implemented 100 embedding size. Embedding size is set to 100, just like here. And then we have in feature as a 32, and we know that the size of the label is 8,929. The setup is basically the same for GRU, except that the bidirectional equal true parameter is enabled for GRU. We need to deep dive on CAML as it is our key model in this paper. Batch size is 32. As we already mentioned, maximum number of words allowed is 500. Embedding size is again 100. Use 50 as output filter size. Size of the label recorded for training is 8,929. And these are the breakdowns of our parameter grid, which is pretty much self-explanatory. From the model result, we know that CAML was the best performer in pretty much notably in terms of macro AUC and also in terms of micro F1 and macro F1 as well. So we note that for the macro AUC, CAML reached 0.97 for average value on test set, which was the highest among all models on test set. Not only for AUC, but also for F1 score, CAML was the best performer out of three. And from the graph, we note that loss for each model is becoming smaller as APM increases, for sure. And to counter overfitting issue, we implemented severe initialization It's also worth noting that the top 5 ICD code predictions are actually identical for CAML and GRU, but LSTM had one different ICD prediction, which is basically 96.04, which wasn't top 5 for either CAML or GRU. So for the summary of our findings and also our research, we used the multi-label classification method, CAML, GRU, and LSTM. We learned that configuring layers and corresponding parameters for each model is a very important step and very crucial to understand where models produce the highest F1 and AUC. We learned that big data pre-processing tools such as Hadoop and PySpark are very important. Severe initialization is very critical to counter overfitting on training dataset because of improper initialization from the beginning. And embedding size maxed out to 1000 and batch size to 32 to fit in GPU memory, and we learned that it's really important to consider these factors due to different computer architectures. Performance metrics calculated as tensor on GPU to avoid the data migration overhead. And again, we learned that the best model was the CAML with macro AUC for average value of 0.971 on test set. For the improvement scope for the next time is that we need a richer dataset with demographic information of the patient to predict the ICD-9 code better. And we may increase the size of embedding metrics to allow more model capacity. And we may use Pareto selection to use the model for highly frequent ICD-9 codes. Train model for more epochs, since we had 10 epochs in this case, and we probably need like more than 10 epochs sometimes. ICD-9 codes grouping as a pre-processing step to predict the group and then individual models for added granularity. We may change the model architecture to current state of the art. Thank you for listening. This is Andy Asang Yunhuan.